We'll ask the next speaker, Viviane Aubin from NTNU, who's going to be speaking about the impact of environmental constraints on using hydropower flexibility and integration in wind and solar.
Hello, everyone. So we'll talk about environmental constraints and hydropower flexibility in Norway. So presentation will go as follows. I will give you a little background, present the methods, some preliminary results, and conclude. So I think you all already know hydropower is in the middle of a very complex environmental dilemma. So we have flexibility in storage and low carbon generation on one side. On the other side, we have impact on the local environment. And in between, we have the environmental constraints that try to mitigate those impacts. There's a lot of research on environmental constraints because it's quite a complex topic. And among those, there's the Sum Effect project at SINTEF that looks at the global impacts of on the Nordic power systems of new environmental constraints on Norwegian hydropower. So in the upcoming years, we foresee a lot of revisions of hydropower licenses in Norway. So it's a good opportunity to modify the environmental constraints and possibly make them more stringent. So the Sum Effect project has created an estimation of those new environmental constraints. However, they could have a different impact when we reach a state where we have a lot of variable renewable energy sources in our power systems. So I will use the VRE acronym for that. And so this study looks at the impact of those new environmental constraints on hydropower, so the impact on the power systems with large shares of VRE. The method used is based on the FANSI model, which is a scenario fan simulator developed again by SINTEF. So it simulates a large number of scenarios with stochastic optimization. So here the problem is defined with 35 weather years, which impact load, water inflows, and VRE production. We have a 3-hour time step resolution, but we divide the problem in weekly stages. And we also have a zonal model, which means that the geographical scope is divided into areas. And as you can see on the figure in the bottom right, it's quite precise over Norway and also over Sweden. So how it works, so we divide the problem in a series of 2-stage problems. So the first stage is the first week, and the second stage is the rest of the horizon, so quite a large number of weeks. And so we're trying to optimize the hydropower production in the first week, given the uncertainty in the following weeks. So we have this rolling horizon. So once we've figured out the generation profile for the first week, then we move to the second week, and then we again have this 2-stage, so the first week and then the rest of the horizon. And then we move like this throughout the whole horizon. And we want to look at high shares of VRE. So we set the study in 2050, where we consider that, or we assume that there would be the energy demand would double in the Nordics, and that would be compensated completely with an increase in solar and wind power. To cope with this this large increase in demand and production, we adjusted the transmission. So we didn't increase the transmission capacity between countries because of the political hassle that is usually related to it, but we'll do sensitivity analysis on that assumption. But we did increase the transmission capacity inside a country. And we calibrated this increase in capacity based on the number of congested hours and also the price correlation between connected areas within a country. So we're setting the study in 2050, but in 2050 we consider two scenarios. So one first scenario, which is the base case, where we have the environmental constraints as they are implemented today, and the second scenario is the scenario with the sum effect environmental constraints. So the major item in those new environmental constraints is to have a revision of the minimum bypass flow, which is locally determined at each site based on few factors. So we have the preservation value of the local environment, if the biodiversity is especially endangered or especially precious. We have the gradient of the bypass, so the steeper it is, the more water we need to keep connectivity. We also consider the energy equivalent of the reservoir water content. So the higher it is, the more valuable the water is, so the less we want to spill in the bypass. And then, based on those three elements, we, I say we, but it's the sum effect project, they came up with a factor, multiplying factor that they put to the natural inflow profile. So they take the Q95, which is the minimal flow that is in the river at least 95% of the time. And so they multiply it by a factor determined by those three first other elements. So with this, we have about 400 power plants that are impacted over 1,700. So it's quite significant. And in those constraints, there are also some modification for the reservoir filling period constraints. But the major element is really the minimum bypass flow. So that was for the method. So some preliminary results for this study. So I'll show you a couple of some graphs. So on all graphs, it's aggregated over all of Norway. And the blue lines represent the base case, so with the environmental constraints as of today. And the orange lines represent the case with the new environmental constraints. So if we look at the first graph on the left, we have the weekly storage percentiles, so how much water we have in the reservoirs. So we have percentiles 15, 50, and 85. And what we see is that for all those percentiles, we have slightly higher levels in the reservoir with the new environmental constraints. Why so? Because those new environmental constraints give higher value to the water because we need it for the generation, but also for fulfilling the constraint. Now, if we look at the generation, we have a duration curve on the right, which shows that there's a slight decrease in the number of hours with high generation because of the water that we have to spill or that has to go in the bypass. Now, if we zoom a bit more on the production, so where do we have this reduction in generation? On the left, we have the weekly average generation profile for both scenarios. And on the right, we have the difference between those two curves. So we see that actually we have a reduction in generation at the spring flood and at the end of autumn. So at the spring flood, what's happening? Well, in the base case, the model has low price sales just in order to, because of the flood, it's just a strategy to make sure that there's no spillage. So the model is ready to sell energy at lower prices just to control the water content of the reservoir. But then if we already have a bypass constraint, then the risk of spillage reduces. So there's no need for additional unnecessary spillage or unnecessary sales. And at the end of autumn, there's also a bit less production because we have to be prepared for the winter where there's high price sales. And that is in addition to the bypass constraints. Now, if we look at the power system, we want to know what's happening for the whole region. what we see is that it doesn't have a big impact, even with all the renewables. So here we have duration curves for the prices. And the horizontal lines are the average over the 35 weather scenarios. So it's hard to see the difference between the lines. So we see that, prices are barely affected. So if we want to have a better insight, it's good to look a bit more at the numbers. So if we look just at the production, because of this bypass minimum flow constraint, we lose some energy, so we lose some production. However, if we compare the loss in production to the relative loss in revenues, we see that actually hydropower uses its flexibility to compensate for the energy loss. So because if we look at the captured price by hydropower compared to the average price, it's higher. So basically, hydropower moves itself to higher price hours. So in conclusion, what we see now is that with those new environmental constraints, we have energy and revenue losses for hydropower, but the revenue losses remain quite limited as it's mostly low price sales that are reduced. The hydropower's flexibility doesn't seem too impacted by those environmental constraints, and it seems that the high VRE power system is able to cope with those constraints. However, we'll have to investigate that further with, among other things, sensitivity analysis. But still, we can ask ourselves, could there be room for even more stringent environmental constraints without disproportionately affecting the power system? So future work will try to look at that. So we'll adjust a bit the modeling of the power system, test more stringent environmental constraints with different types of environmental constraints, and also perform some sensitivity analysis. So that's it. Thanks.